Our next speaker is Axel Guinot from the Carnegie Mellon University, and then he'll talk about like weak lensing with Roman from galaxy shapes to shear measurement. It's all for you.
Okay. So hello everyone, I'm Axel Guinot. I'm a postdoc at CMU, and today I'm going to talk about how we're going to do weak lensing cosmology with Roman. So first, a little bit of introduction on gravitational lensing. So this is an observational phenomena where if you have some background galaxies and you overimpose very massive galaxies in front of them, what you're going to observe is some gravitational arcs that are forming. And so that's what we call strong lensing. But as I said in the title, what I'm interested in is actually weak lensing. So my way to introduce that is we look at the same phenomena, but this time instead of having very massive galaxies, we have a galaxy cluster. So of course clusters can also create strong lensing, but they can also make weak lensing. And so here we see a very slight deviation of the light profile of galaxies around this cluster. And one way to look into this is by, for example, making mass mapping, which basically tells you the distribution of dark matter in the universe. And so finally, I'm going to quickly introduce cosmic shear, and so this time I don't have an animation for that. And so basically here the idea is to look at an effect that is even fainter than the previous one, and this time we're looking at how galaxies, taking them by pairs of a given distance, are actually the shapes that are correlated with one another. And so if you look at that with different separation between galaxies, you can actually reconstruct what we call two-point correlation function, and based on that we can actually constrain cosmological parameters that we are interested in. So as I said, so we're interested in cosmic shear, and so for that we rely on the measurement of galaxy shapes. But here there is a problem, which is how do we define the shape of a galaxy? So we can try to fit a Gaussian on top of it, but that's probably not going to work very well. But the thing is, we are not really interested in the intrinsic shape of the galaxies, but rather how this shape is modified when you apply the shear. And that's what we are interested in. And so the question is actually our solution. We're not measuring galaxy shape, we're actually measuring the galaxy shear. And so based on this idea, there was a method that was developed called meta-calibration, where the idea is to compute the response of our shape measurement estimator, whatever it is, to an applied shear. And so to do that, the first step is to deconvolve from the PSF, and so the PSF is the optical response of our telescope, and then we artificially apply a shear on top of this object to actually measure our response using some very basic finite differences. And this method actually works extremely well. And so with this, we can account for different things, such as modal bias. As I just mentioned, we don't really care about the actual shape of the galaxy as long as we know how it changed. We can also correct for like noise biases and also selection effect. But of course, what happens if you have more than just one galaxy in your field? And so here, for example, we have an entire scene with many galaxies in them. And so actually the answer to what we do in that case is very simple. We just share everything. And so that's a new method that is called meta-detection, and it was introduced in 2020 and used in DS Year 6, and it's what we are trying to implement for Roman. And so with this approach, we can calibrate for all the biases that we were able to with meta-calibration, and on top of that, we can also include detection bias. So how would that look like in Roman? So we have this process where we first create a coad, then we apply our meta-calibration step, run detection, and then measure the shapes of those objects. But here there is a very key important thing is that, as I mentioned, we need to deconvolve from the PSF. So as you probably know, on Roman images, the single exposures are actually undersampled, meaning that the size of the PSF is smaller than the size of our pixels. So we need to oversample those images, meaning that making the coad is actually pretty hard. And so for that, we have a method that was developed in our pit, which is called MCOM, which can actually make oversampled coated images with a well-defined PSF. And so with that, we can actually apply meta-detection. So now I'm going to present some recent results that we got testing this entire pipeline. And so for that, we use simulations. So here we've came back to the level 1 images that we are simulating with as many instrumental effects as we can And we've been working in collaboration with the SOC to actually do that. And then we are processing them down to level 2. So this is calibrated single exposures, which we then co-add using IMCOM. And so here, as you can see, I'm showing just a simple representation of a level 1 image, and you can see that there is a lot of effects that need to be cleaned up before you can actually obtain a nice coded image. So here on the left, you have our science image. The large hole in it are basically bright star masks that we are adding just to remove the bright stars, which could create some undesirable effect later on. And on the right is the inverse variance map of the noise. And so this is very important because what we can see on this image is basically that the noise is varying very quickly on the image, and that we also have strong correlated noise. And so that can create some issues in the processing if you're not careful enough. And so here I'm just advertising this recent paper that came out that actually explain how we can account for this correlated noise, for example, for photometry. So let's go back to meta detection. So on this simulation, we have around 5 square degrees that have been simulated. We have measured the galaxy density that is above 40 galaxy per arc minute square, which is roughly what we were expecting for Roman. We also have a very good shape noise thanks to space images. And so here I was talking in introduction about mass mapping, and so here I am comparing the recovered mass map from our processed data to the expectation from our input simulation. And we can see that we can recover the signal pretty well, and that we can then trace the distribution of that matter in our simulation. I was also talking about cluster lensing and the tangential alignment of galaxies around clusters. So that's another test that we have performed. So here we just took the true position of clusters in our simulation and measured the tangential shear around them and check if we can recover the expected truth, and we actually do. And at the same time, we can also check for systematic here because we can measure the cross signal, which is expected to be 0 for weak lensing, and that's also something that we can verify. So I was talking about the very nice COA that we can make with IMCOM, but sadly they're not perfect. So one of the problems, it's very time consuming to make those COADs. Also, I mentioned correlated noise, which is an issue for photometry, but also for other things. And another problem is like propagating the single exposure information through the squatting process can be very challenging. And those effects are very important, such as chromatic effect on the PSF or 0-point variations, which could be due to ice, for example. So I've been working on a new approach, which I call meta-coaddition. What the idea is actually to shift a little bit how we do this processing by doing the meta-calibration first and then making the coads. And so this way, we don't need to run IMCOM. Another advantage of this approach is that we can split the analysis by running the detection on the coad only, and then we can do the measurement at a single exposure level, which makes the propagation of any information that we have at the single exposure way more straightforward, such as the chromatic effect or the 0-point variation I was mentioning. And also this processing is significantly faster. So here I'm going to present some very preliminary results with this approach. So I haven't introduced much what we call multiplicative bias, but basically it's just a shift of the amplitude of the 2-point correlation function I was mentioning for cosmic shear in the introduction. And so we want this to be as close as possible to 0. And so here on those very basic simulation that we have been using, it's something that we can recover, so within our Roman requirement. So it's actually a very promising method and that we are continuing to develop. So to conclude, first of all, I'm very thankful for all the work that has been going on in our pit, because developing this pipeline is actually a lot of work, and testing it, I mean, we are still in the process of testing this pipeline and validating it. Our preliminary results on the both simulation and processing from the level 1 to level 2 is also quite advanced. I mean, there's still a lot of work to be done on that. Also, if you are interested in some of this, we have a poster here from Tony about how we deal with cosmic rays, so I encourage you to go check it out. Our result also from the simulation on like recovering The cluster lensing signal is very good. I haven't presented it here, but we are also testing for cosmic shear, and we can also recover the signal. And so, yeah, as I mentioned, we're also developing new methods. So meta-coaddition is one of them, and we can, on basic simulation, recover the multiplicative bias pretty well. And there is another one called effortless that is developed by Kelly. He has presented his poster recently this week, and I also encourage you to go check it out if you're interested in this. And thank you.
All right, thank you for the nice talk. So do we have questions? We have, yeah, so over back there. Laura.
So your meta-coaddition, how deep do you go?
In magnitude?
Yeah.
I think we're reaching around between 25 and 26. I don't remember exactly.
Do you have an SNR cutoff in order to do your rebalancing analysis?
So, yeah, so at the moment I'm mainly looking in the IMCOM coads, and because of the correlated noise, it's a bit challenging to define an SNR. So, yeah, at the moment it's a bit arbitrary. It's something that we are looking into. But yeah, the depth of reaching is between 25 and 26.
Okay.
Okay, over here, in the center. Yeah. 2 questions. Okay.
In your simulation, do you include PSF ellipticity?
So actually for the PSF, we are using the SOC prediction for the PSF model that I've measured in the lab. So yes, there is some level of ellipticity. Also, yeah, it's space PSF, so it's very, very small. So it's more like aberrations more than ellipticity, I would say.
Okay, thanks.
Where are the performance gains coming from? Naively, I'd expect that for meta-coaddition, I mean.
The what, sorry?
The performance gains, like the fact that it's faster, if I understood you correctly.
Yeah.
Did you say that meta-coaddition is faster than meta-detect?
Yeah.
So if I understood correctly, you have to shear each individual exposure. So you're shearing however many more images go into a coad. How is that faster than shearing one image?
It is faster because we don't run IMCOM, and IMCOM is really the limiting factor here. Because the idea is when you run IMCOM, you're basically Gaussianizing the PSF at the same time as you're making the oversampling. Mm-hmm. And so you're solving some very huge linear matrices, and that's extremely slow. So to give you an idea, it takes 11,000 CPU hours per square degree per band. So if you don't do that, you can go significantly faster, even if you shear all the single exposures.
I see.
More questions? I have a quick question actually. So when you are doing the like co-adding all those like oversampled images, there's no guarantee that all these oversampling factor for each field is actually same. Like sometimes it's kind of 2, sometimes 4. So do you have any ability to actually co-add them together, or?
So yeah, the oversampling is always the same. It's fixed. And I think the limiting factor is the number of exposures that you have at each location, and this is more or less constant in every band. So yeah.
Okay. We have time for one more question, maybe. If not, okay. Let's thank to the speaker. Thank you.